Okay. Hi everyone, welcome to the Institute of Data Science and AI seminar. It's a pleasure to introduce Dr. Edward Salakpi from Sterling University, who's going to be talking to us today about forecasting drought in pastoral communities. Dr. Salakpi has an undergraduate degree from the University of Ghana in agricultural science, an MSc in information systems, specializing in data mining and information systems architecture. And he combined both of those areas of expertise into his PhD at the University of Sussex, which is on Earth observation for AI applied to agriculture. So, welcome, Edward, and
thank you.
Take it away.
All right. So, hope you can all hear me very clearly. Hi, everyone. So, my name is Edward, and this afternoon I'll be taking you through a short presentation, not too short though, on forecasted vegetation condition, or what we will from now on refer to as drought, in pastoral communities, especially in Kenya, where my PhD research was conducted. So I'll start by just, giving some little information about myself. Sorry. Yes. So, like Anna said, I got my PhD from the University of Sussex. Prior to that, yes, I did my undergraduate at the University of Ghana and then my master's at the University of Reading. And for my PhD, I did that at the Physics and Astronomy department in the University of Sussex. So I like to think of myself as an astronomer, even though I was the only astronomer in the department looking down at Earth while everyone was looking up. And my research focused basically on using Earth observation to monitor vegetation dynamics, then also for monitoring drought and then also forecasting drought for early warning. Currently, I'm a remote sensing scientist with the Fourth Era project at the University of Stirling in Scotland. So that's just a little bit about myself. So I'll jump right into the presentation. So for today's talk, I'm going to give a short background on what drought and vegetation stress is all about. Then we'll talk about the role of Earth observation, how we can use Earth observation to address the issues of drought. And then I'll talk about some of the work that I did during my PhD research and some of the models that I used and some of the results, talk about how I evaluated my results and some of the outcomes that we got from that. And then from then I'll move on to, so, after doing all this work, then what next? Or why do we do all this work? So I'll talk about some policy implications and then also future work and then conclude. So I'll first of all start by giving a background about drought. So drought events are one of the most prevalent, disasters around. You hear drought occurring almost everywhere in the world, and it's always been reported in some journal or some news letter or something. And one of the continents that are most hit by drought is in Africa, especially in the eastern side of Africa, where they have very unstable, seasonal weather or weather and seasons. So the seasons, even though we have some laid out seasons, sometimes they tell you the long rain season is in March, April, May, but then long rain extends over that period and you have some flooding. And then also they tell you the dry season is around October, November, but then you realize the dry season extends sometimes from July all the way to January and all that. And so very erratic weather patterns. And so drought is always prevalent in such regions. And but then when we're talking about drought, you can categorize drought into 4 types. So we have the, sorry if my mic is so we have the meteorological drought, which mainly is caused by rainfall deficit. So whenever there's prolonged periods of no rainfall, you always have this kind of drought referred to as the meteorological drought. Then we also have the hydrological drought, where people who are monitoring water bodies, lakes and streams, whenever there's a reduction of water flow in the streams or lakes, they refer to that as hydrological drought. And then we have another type called the agricultural drought. And this one has to do with the shortage of water available to plants and crops. And that is where my research focused on, because this is directly linked to us as people, because agricultural drought affects our livelihood, affects what we eat, how we live, and all that. And then finally, we also have socioeconomic drought. Now, this one usually comes up after you have some meteorological drought occurring, and then some agricultural drought occurring. Then you have that impact of those drought on the socioeconomic life of a region or a country, or people. And that is when you say we have scarcity of goods, and this is usually linked to some drought event happening. And so that's when we term that as socioeconomic drought. But then coming back to agricultural drought, why is it so important? Well, it can be very devastating, actually, because if you look at some droughts in 2014, 2016, I mean, you could see from the pictures on the slide that people actually lost their livestock because there was basically no water, and then no crops or no vegetation or green fodder for the animals to feed on. And so animals lost weight, and some of them died from dehydration and all that. Now, these affect livelihood, especially in the arid and semi-arid regions, which are the ASAL, which are also termed the ASAL region, because these regions depend on agro-pastoral activities and is the major contributor to their food and then also their income. And so when this drought occurs, it really impacts them severely. Why these impact them is mostly because when agricultural drought happens, is the grass, shrub lands, the green fields, the rangeland where they send the animals to feed. Those are the places that suffer this kind of drought, and people who don't find anywhere to send the animals to, as you can see in the image. And so animals don't get food to eat and they die, or sometimes it leads to loss of income. So then what is the way out for this? One of the ways that they thought could help, mitigate this problem was to come up with what they call the early warning systems. So, and in fact, the SDGs recognize early warning system as one of the systems that when put in place, could actually solve the problem of drought. And research has also shown that usually when you have early warning systems in place for any kind of disaster, it's 20 times more cost effective than post-disaster relief. That's waiting for a disaster to happen before you send relief is always more expensive than if you're able to anticipate that this is about to happen and you take an action earlier to prevent it or to do something to curb the adverse impact on people who are likely to experience or suffer from it. And so they saw early warning as the way to go. But for drought, usually for early warning systems, you need to have very good meteorological services. You need to have some met stations well situated around places where these drought occurrences are prevalent. But then in developing countries and in places like East Africa, you don't have a lot of those weather stations all around, and you don't have the data that you need to be able to help you adequately or accurately anticipate drought before they happen on time. And so one of the ways that we've thought of dealing with this is to work with what Earth observation data. So Earth observation, basically also known as remote sensing, but because people have adopted the term Earth observation because remote sensing can be applied not only on Earth, but then you can actually have, because we now have satellites also monitoring the moon and other planets, and then taking images of those things. And so if you stick to remote sensing, it becomes a bit confusing. So then came the term satellite Earth observation to make it more specific that our focus here is observing the Earth. And usually this is done by using these instruments, right? I'm sure a lot of you are astronomers, and so know a lot about these things. But then these satellites are launched into space, and they have very huge, imaging devices on them that are able to take pictures of the Earth. And from this images, we are able to collect a lot of data. So you can collect data on people's farms, how crops are faring over time, because these data sets are collected at regular intervals. So we have some of them collected daily, some of them bi-weekly, some of them monthly. And so you can study the trends in these images and also get some information about what is happening on the Earth's surface. So some of the data sets that some of these satellite Earth observation instruments provide are temperature. We have some information on weather and climate, like hurricanes and rainfall. And then also it collects reflectances that you can use to deduce or derive vegetation indices to monitor vegetation health on the Earth's surface. And that is where a lot of the work what I'm going to talk about today focuses. But then the question is, how does these satellite Earth observation instruments, capture the data, and then how do we use such data for meaningful, work or meaningful data analysis? So usually these satellite images capture. So there are about two types. There are two types of these satellite images. We have some that fall along, fall in the category called the passive ones. So the passive ones, they are just like your phone camera that take pictures of the Earth. Basically, they rely on the light that is being emitted by the sun or whatever radiation is coming from the Earth's surface. And they use that to capture the images of the Earth. We also have some which fall in the category of the active Earth observation, which use radar satellites. So they shoot radio waves and then try to capture the backscatter that is bounced back from the Earth and then use that as information. But then for what I did, or for what I'm going to talk about today, I'm going to talk about the passive ones, which are also known as the optical satellite. These ones, they rely heavily on the radiation that is coming from the Earth's surface. So, reflection of light that is bouncing off the Earth's surface. And usually when they capture the images, the images are captured along the electromagnetic wavelength bands. And so you have images being captured within some wavelengths. And if you take our phone cameras, for instance, usually they capture images in just 3 bands: red, blue, and then green. But then this instrument aboard the satellite images, they're able to capture images along wide range along the electromagnetic spectrum. So they have images being captured in the blue, green, red, and then also they have to able to capture images in the near infrared, and then also shortwave infrared, and then with the radar satellite, then we go into those X-ray and those other wavelengths. But for optical, they usually capture images within these wavelengths, and depending on what you want, you combine these wavelengths in some mathematical formulas to be able to get some information about the Earth's surface. So, like you can see over here, this is like an example of images that have been captured by this instrument. And so in my case, for instance, I did a lot of work with vegetation health. And so one of the indices that I was interested in was what they call the normalized difference vegetation index, which is calculated from a combination of some of these bands. But why these bands are important is that usually if let's say you take some stack of images that have been captured by the satellite and you just maybe sample a pixel and then you look at that pixel along all the bands, you could see that in some bands, the reflection from the object on the Earth is higher and in some bands is lower. And so to actually, if maybe you are interested in monitoring water bodies, for instance, you realize that the water bodies are not very visible in the blue, but then usually in the green, there's some high reflectance over there, and then it quickly drops by the time you get into near infrared. So if you're interested in water bodies, then anything beyond near infrared is not a good, any band beyond the near infrared is not good. If you're interested in, let's say, soil moisture, for instance, or soil, you can see that reflectances are quite low within the visible, what we usually see when we look at images, the RGB, but then they are very high in the immediate to medium infrared bands. When it comes to vegetation, plants, crops, a lot of the light is absorbed for the photosynthetic process. And so when it comes to blue, green, and then some part of red, it all absorbed for this photosynthetic process. And so there's low reflectance in this area. But then if you move into the near infrared, you see that or if you move from the red edge or to the near infrared, you see a very high reflectance. And so to actually capture information on the plant health, then we we have to choose bands that show, very high reflectances. And so, for instance, to get, a healthy plant, you would see that the near infrared would emit about 50%. A very good healthy plant would emit high, near infrared, and then also some high, some not very high, but then some low red information in the red band. And for a plant that is not too healthy, you get some low near infrared and then also very high red, something, not too high, but then some good reflectance in the red band. So to actually capture the health, then you use this formula, which is basically taking the near infrared, subtracting the red band, and then normalizing it by adding that. And then you get this index, which is called the normalized difference vegetation index. Now, a high value of the NDVI means that, plants are healthy. A low value means plants are not healthy. And this is just one of the indices that you can compute by combining some of these bands. For this work, for instance, which we talked about drought, we used an index called the VCI, and the VCI is basically derived from the NDVI. So anytime you calculate this NDVI that I demonstrated earlier on, and if you wanted to know the VCI, so VCI is an agricultural drought indicator. So it tells you the drought condition at a particular point in time, given an NDVI value. So you take the NDVI value for a particular point in time, you subtract the long-term or the multi-year minimum, and then you also normalize that by just subtracting the maximum and the minimum from, and dividing that by the difference between the maximum and the minimum. Now, the maximum and the minimum here, they are long-term maximum and minimum. So what you do is you take a period of interest, maybe the year 2000 to maybe 2018, and then you take, if you are working with weekly data, for instance, weekly images, you take the minimum and maximum for all the weeks. So if it's week 1, all the week once in that period, you take their minimum. All the week once also you take their maximum, and you do that for all the weeks. So week 1 to week 52 for the whole year, you take the minimum and maximum, and then you use that in this formula to calculate the NDVI. So what it basically tells you is that for every NDVI value, you're looking at where it lies within some drought range. And usually the VCI values range from 0 to 100. And if you calculate this and you have VCI values between 50% and 100%, then that indicates that you have a wet condition and there's basically no drought. And usually if you have something ranging between 50 and above 35, then we have some normal conditions as well of no drought. But as soon as the VCI values hit 35 or below, then you are approaching some drought condition, or let's say you're approaching a condition where your vegetation in the area where the image was taken is being stressed, and so it calls for some attention because you're approaching some drought condition. And anytime it falls below 10, you should know that then you are like in very severe drought conditions. And so that is how we measure drought using the satellite images. NDVI, VCI are just an example of some of these indicators that you can derive from satellite images. We have a lot more, as you can see in this list over here. We have other indicators like the Enhanced Vegetation Index, which is an enhanced form of the NDVI, because usually NDVI doesn't do well in areas with very high plant saturation, like in forest areas or dense woodlands. And so they developed this new one, which is Enhanced Vegetation Index with some correction factors, but it's still a combination of the band, but then with some correction factors so that you can see vegetation health in dense wood areas. Now, in areas where there's sparse vegetation, like in deserts or places that are close to being, or places that have a lot of background soil effects, we have this other vegetation index called the soil adjusted vegetation index, which also has some correction factor for the background soil. And this is also just a combination of some bands together. And one other interesting thing you can actually get from this satellite images too is the normalized water index as well. And these ones come in two forms. There are two types of this normalized water index. There's one that tells you the amount of moisture in the ground or amount of moisture in some water bodies, not amount of moisture, but then it tells you the level of moisture in the soil or in some shallow water bodies around the Earth's surface. And then there's another NDWI that also gives you the amount of information on the amount of water in a plant. So if you wanted to know the amount of moisture in plants also, there's a way to combine these bands to get NDWI for that as well. Another thing you can also get is, well, some of this satellite also have this thermal instruments on them that are able to capture what they call the temperature brightness, and that those are converted to land surface temperature. So we have satellites that are able to give you temperature, like I said earlier on, and you can actually combine those LST bands in a way, just like the VCI, to also get another index called the temperature condition index, which is also another drought indicator. And then you can combine VCI and TCI as well to get the vegetation health index. So basically, these are some of the indices that you can derive from satellite, and it gives a lot of information that you can use for monitoring the Earth's surface for anything that you think you might be interested in, any biophysical indicator that you think you might be interested in. Now, what are some of these applications of this satellite Earth observation data sets? So in the area of analytics and machine learning, usually analyzing or working with satellite images fall within two categories. We have the geographic object-based image analysis, and these ones usually deal with you using sections or group of homogeneous pixels, or pixels that look the same, that you can, when you take those pixels like you're seeing in this image, when you take those pixels, you can tell that there's something over there that is an object and not just some pixel value. But then you can tell that, okay, because these pixels are homogeneous, that means they have the same value or they have the same reflectances. You can tell that is an object, and you can, with those ones, you can apply some convolutional neural network, any of this computer vision tools, if you have some high def images or semantic image segmentation to them, to actually be able to do some land cover classification or mask out some land cover artifact that you're interested in. So for instance, in this one, this is an example of some work I did in Costa Rica, where I was trying to map banana plantations. And so in this case, using some machine learning approach, I was able to map out, where the banana plantations were in a certain field or in a certain area of interest. Now, another way you can analyze this satellite Earth observation data sets is to use the pixel-based approach. Here, we just extract and analyze the pixel values or the reflectances, because if you know, the basic unit of every image is a pixel, and these pixel values from satellite images are basically reflectances or levels of reflectances from the Earth, or from the light being reflected from from the sunlight or something. And so these pixel values, you can capture them at a point and then plot them over time to see how these pixel values are changing, like you can see in this image. And you can use that with models like linear or logistic regression, random forest, or SVMs to do whatever analysis or whatever machine learning predictions or whatever it is you want to achieve with some form of analytics or machine learning or any statistical analytics as well. And so these are ways you can use this satellite data sets. So coming to the work that I did, then how then did I use all this in my research? At this point, I'll just touch a bit on forecasting vegetation condition. For my research, I worked in a group at the University of Sussex, and we used various methodologies in trying to see how well we can take the satellite images and then forecast some vegetation condition, which we are terming as drought. And all this stemmed from the fact that sometime in 2017, one of my supervisors went to Kenya to go and study how they were monitoring their drought, and they were using these indicators. They were using VCI, to be specific, which was derived from NDVI. By the way, VCI, like I said initially, can also be derived from other indices like the SAVI or the EVI, if you think those ones will be more relevant to you. So VCI cannot just be derived from NDVI. But then in Kenya, they were using NDVI-based VCI, and we realized that a lot of their anticipation of drought were based on expert judgments. And so they calculate VCI for today, and then they said, okay, based on VCI for today, maybe next week there might be a drought, without putting it into any form of model to see if they could forecast that. And so this is what sparked the whole idea of trying to see if we can use some form of machine learning models to forecast, so that they can have some empirical way of telling that or forecasting drought in some 2 or 3 weeks or in a month's time. So some of the methods that we applied over here were, we used Gaussian process, we used the auto-regression methods, we also used Bayesian auto-regression distributed lags, where we used a lot of lags, where you look back and take values from the previous time point and try and see if you can use that to build a model to forecast the same value into the future. And then also we went ahead to also do some form of hierarchical Bayesian modeling, where we try to incorporate the spatial differences within a given region. So subsequently, in subsequent slides, I'm going to give more details on how all these things work. So for that research, we used data, not only the reflectances like I was telling you about, like those are the red, blue, green, and all those infrared, but then also we worked with precipitation data, which were also derived from satellite Earth observation data. We also use some soil moisture data, also derived from satellite Earth observation. These ones were mostly derived using the radar satellites I was talking about earlier on. And this one was produced by a group called CHERPS, and this one was produced by the European Space Agency under the Climate Change Initiative project. And so we use this project, we use these data sets in combination, we combine them to try and see if we could study and understand vegetation dynamics on the Earth's surface, and then also see if we can put them in some of these models to forecast this vegetation condition index that I spoke about earlier on. Now, prior to using the data for the modeling, we had to do some data pre-processing. And so usually one of the biggest challenges when you're dealing with optical Earth observation or the passive Earth observation is cloud. So anytime you're taking, the instrument is passing over the particular section of the Earth and it takes an image, if there's a cloud between the instrument and the land surface, then you're going to have some missing data. And so we always had to do some cloud masking to first of all take out the cloud data, because that's not what we want. And then these usually leave some gaps, and then we usually find a way of filling these gaps. But here, to just give you a heads up that the gap filling we did over here was not the special kind of gap filling, but then we did just gap filling after we had extracted the time series data. Because a lot of the work we did here were based on the pixel-based, image analysis and not the object-based image analysis. And then we also did some, because it's pixel-based, we also had to apply some smoothing algorithm to just make sure we reduce some of the noise in the data. And like I said earlier on, a lot of this work was based in the arid and semi-arid regions within Kenya. So the first work that we did was to use Gaussian, try and see if we can use univariate data. So in this case, what we did was to just extract VCI and then try and see if we could use, and VCI, like I said, is commonly used by the National Drought Monitoring Agency, which is an agency in Kenya that monitors droughts. They use this for monitoring drought, but then they didn't have any forecast models in addition to their, they were not reporting any forecasts because they were not using any forecast models. And so we also decided to then use the same thing and not bring in any other foreign index for them. So that's why we stuck to the VCI and based on the NDVI. I mean, of course, we could use other forms of, we could have used other forms of other indicators, but then because we wanted to just continue using what they were used to, be stuck to the VCI. And what we tried to do was to use historical values of the VCI only, because VCI, one of the properties of VCI is that it has this strong persistence. And so if you know VCI from 2 weeks or 3 weeks ago, it's easier to put it in some auto-regression model and then forecast and see what VCI is going to be in the future. So what we did was to use Gaussian process. Now, not to go into much detail, Gaussian process is basically it's a form of an advanced regression, let's say, but then what you do is you're trying to fit some data to a series of Gaussian distributions. And usually what happens is it's a non-parametric model in which means you don't really need to learn some parameter that you can store and use in the future. It learns the parameters on the fly and then uses that for your prediction. So what the Gaussian process, when you run it, does is that for each consecutive point, it tries to learn the correlation between them and then stores this correlation between each consecutive time point. And then what it does is if you want to extrapolate the data into the future, then it uses this information that is learned from the correlation from or the covariances between the data points to actually make future predictions. And so, and usually to compute this kind of covariance that is used by the model to make the predictions, we use some kernels, and for our work we use the RBF kernel for that. Now, to compare the results from that to some baseline model, we also use the auto-regression model where we use a lag of 3. So for auto-regression, we are trying to basically do the same thing, use VCI to forecast VCI. So we had this regression where we were regressing VCI from 3 weeks ago to future VCI. So if you wanted to forecast VCI maybe 2 weeks ahead, you look at VCI from 3 weeks ago and use that to forecast. And if you wanted to forecast 4 weeks ahead, you look at the same VCI from 3 weeks ago to forecast that. And so that is what we basically did. And so for the regression, we use this formula here where and this is a parametric one. So basically what we are trying to do over here was to see how we can learn this parameter here and how that parameter affects or changes the lags affect the lags in the VCI. So here X represents the lags of VCI, and we are trying to forecast VCI at a time point ahead. So I didn't want to mention, but I just wanted to bring this so that people will understand how the model was trained and how we got the results, and then we evaluated them. So to actually run after pre-processing and after writing the scripts to run the model, what we did was to chunk our data into pieces, into splits. And so what we did was to make sure that we don't, first of all, overfit the data. We make sure that the model is generalizing very well and making accurate predictions. We split the data into chunks, and then what we did was for each split, we trained the model on some section of the data. Then we forecast. Then we leave a section out to make the forecast, right, which is the test set. And then the actual observed data for this test set is also reserved and then used for evaluation. So we hold it out and then we use it for evaluation to see if the predicted set, which is this orange side, is actually being predicted with some accuracy compared to the data that we held out. And so we did that for different sections of the data, and we split the data, and we use what they call a rolling window cross-validation. We take a section, we train on part of it, we forecast part of it, we move to another section. But then what you realize is that at every point in time, we are having this data also is now coming here, and it's also being passed to the model for training, because we wanted to make sure that the model had seen enough data to train on so that it doesn't overfit, basically. And that is what we did. So jump into some of the results from the Gaussian process and the AR model. Here you can see a contour plot over here that is basically like a scatter plot, but then with some contour lines, just showing the level of correlation between the true VCI and then the forecasted VCI. So this is for 2 weeks ahead, where we are trying to compare the forecast VCI and the true VCI, and you could see that from this, you could see that compared to this straight line over here, you could see that there was a strong correlation between our forecast and the R2 score over here, which was one of the metrics we used to measure the accuracy of the model, was 0.99, which was very high for 2 weeks. And if you consider that VCI values range from 0 to 1, then you get an RMSE of 1.8 could tell you that the error or the residual was very low in this case for the Gaussian process. And you could see a similar thing for the autoregression model as well. And you could see that the model generally did well for prediction up to about 6 weeks, where as at 6 weeks, we're still getting an R2 of about an R squared of about 0.88, which is also very good, because usually if you read literature, anything below 0.7 is not considered to be very accurate whenever you're using this. Well, it could be accurate, but then not considered as having very strong accuracy if you're using the R squared evaluation metric. And so getting values above 0.7 after 6 weeks show that the model was doing very well. And for people who might be confused about how this R2 metric and the RMSEs were calculated, this is the formula that we use. We actually use the observed data minus the forecast data, and then also we divide that by the variation within the data and then the variation within the forecast. And so the variation within the data is minus the mean, and then that of the data minus the true observed minus the forecast. And then also for the RMSE, we'll basically just observed data minus the forecasted data all over the total number of so that is one that the models were doing very well. At some point that sorry, I hear my internet has gone now. Can you still hear me?
Yes, we can still hear you, Eddie.
We can. All right. So let me just continue then. So moving on to another metric that we used to evaluate the model. One other metric we used was the ROC curve. Usually you don't see ROC curve being done for regression tasks, but then what we tried to do was, because we know that VCI, anything below 35 indicates a drought, what we did was to take the output of the prediction and then put it into a binary. So anything above 35, we made it a 1. Everything below, no, everything above 35, we made it 0. Everything below 35, we made it a 1. So the 1s mean drought events, 0 means no drought event. And then we try to use that. We look at the calculated the hit rate and then the false alarm rate for these predictions from the models. And you could see that the model was still doing very well. And why we wanted to do this was that if you are going to present this model to an agency like the NDMA in Kenya to use, you need to prove to them that your models are predicting very well and they're actually able to capture drought events very well with very low, false alarm rates. Because what you don't want to do is to raise an alarm that it's going to be a drought, and then you end up putting in raising all your funds to go, deal with the issue, and you actually go there and there's no drought. And so we wanted to make sure that what the models were saying were actually true. And so in this case, you could see that anytime let's say at 2 weeks, for instance, when we predict that there's going to be a drought, there's about almost 98 to 99% chance of that happening. And the chance of that being a false alarm is very low. It's not even up to 1 or 0.1. And you could see that after 6 weeks. And then you could see the same for the AR, but then you could see that for the autoregressive model, it had across the lead time, which is 2 to 6 weeks, you could see that it had some high hit rate values compared to Gaussian process. But then one thing with the Gaussian process is that because it's a non-parametric model, it tends to be more robust, whether you take a pixel from the northern part or the southern part or whatever. But then for the AR, what we realize is that because you are learning just one parameter and using that to make predictions for all other areas, you usually get some areas not having very accurate results. And so at the end of this, I'll show you that in for Kenyan Drought Monitoring Agency, they preferred the GP, and so we actually had to put in a GP model for them that they are using currently in production for drought monitoring. So the GP and the AR models, as you can see, were very good. They did very well for short range forecast, that's 2 to 6 weeks. But then for drought early preparedness, preparing for drought and going to address the issue of people who are about to face drought, it's good to have longer lead time. So you don't want usually because of bureaucracies in some of these systems, to get the funds and whatever mitigation measures you need to go and address the issue of people who are about to be hit with drought. It takes some time, and so usually some of these drought monitoring agencies prefer models that are able to give you forecast over longer lead time, so beyond 6 weeks. So And then we also from literature, got to know that, I mean, this is obvious, everyone will know that usually for plants, vegetation, it's usually affected by other factors like precipitation, soil moisture, temperature. And so what we did was to set another research question, which we were asking ourselves, so can we improve, the previous models that I just showed you, that's the GP and the AR autoregression, can we improve them by including other exogenous factors like soil moisture or precipitation? And to answer that question, we considered using an autoregression distributed lag model. Now, this autoregression distributed lag model, basically what it does is to distributed lag, because you tell yourself, okay, I want to forecast a particular index, maybe 2 or 3 weeks ahead. How far back can I look? So how far back are those lags distributed lags that you want to use? And I also want to bring in some other factors, like not only the indicator that I want to focus on, I also want to bring in some other factors that I know also affects that indicator that I want to focus. And so what the auto-regression distributed lag enables us to do is, like I said, it's a generalized form of the AR model, but then this is for multivariate time series analysis. And so what it helps you to do is to bring in other variables. And so it enables the dependent variable, which is in this case is the VCI that we want to forecast, to be modeled as a function of its own lags. So that means you bring in the function of you bring in the lags of VCI itself, just like we did with the AR. But then also you can bring in the lags of, additional explanatory variables, like lags of soil moisture and the lags of precipitation. And what we did was, because this method was more similar to the AR or the autoregression model, what we did was to use the AR as a baseline for this. So we used this model, and then we compare the output of this model to the AR model. Or we compare the output of the BRDA model to the AR model. But then we just didn't use the autoregression distributed lag as it comes, because usually these models are usually you calculate you can see how the formula is, and usually to be able to use this model, you need to put it in some form of a framework to get either using ordinary least squares or maximum likelihood to actually get these parameters that you're then going to use to make your prediction. But usually when it comes to forecasting, people are interested in forecast uncertainties and then also the reliability of that forecast that you're making. And so we decided to use this or implement this autoregression distributed lag within a Bayesian context. And why did we use the Bayesian context? So the Bayesian context enables you to, first of all, bring in some prior knowledge of the model parameters. So if you work with this data for some time and you know that, okay, parameters are likely to be within this range, you can actually put some priors in the framework before the model actually sees actual data and actually learns the actual parameters. Parameters are also approximated using some Markov chain Monte Carlo algorithms, and usually these algorithms are known to be robust and are very good at sampling parameters from any given parameter space, or if you give it some data, it's able to do some very good parameter approximation. And one other thing with this Bayesian framework that makes it very useful is the fact that the inferred parameters, or whatever approximated parameters, which are usually referred to as the posterior, come as a probability distribution. So instead of getting just one value for your parameter, you get a distribution of parameters, and this enables you to easily quantify, the uncertainties around the prediction. And so you can get that, okay, this if I take the mean of that whole forecast distribution, this is the actual forecast value, but then that forecast value lies within this range of forecasted values. And so you can say that, okay, my forecast is 36, but then it has a minimum of about this, or can have a maximum of about that. And so usually this is how these Bayesian models work. Before you actually train your model, you set some prior belief about some prior belief about your model parameters. You give it some data, and then it runs the MCMC, and then it tries to now update that prior knowledge that you've given it based on the true data that it's seen. So it updates that, and then using the likelihood function is able to then get the posterior belief, which is actually what the parameters are supposed to be given the true data that it has seen. But then I know a lot of people who might not be who have not had the chance to be introduced to this Bayesian context to understand how this fits into the whole, Bayesian or the autoregressive distributed lag formula. So this is like a shortened form of the formula where we are trying to find some VCI at a time point ahead, but then we are looking at some VCIs of lags of VCI, lags of soil moisture, lags of precipitation. What the Bayesian model is, what the Bayesian framework is basically doing for us is to help us calculate these parameters so that we can make this prediction. So it's not the Bayesian, what people, or what, when I started my PhD, when they were talking about Bayesian, to tell you the truth, when I started my PhD, I didn't have a lot of understanding of this. I thought that, well, this Bayesian model that was going to make the prediction for me, but basically the Bayesian models, what they do is to help you estimate this parameter that you're going to use for your model prediction. And so to situate this within the Bayesian context, then you are trying to solve some probability problem. And the problem I've had to solve over here is that, okay, what is the probability of my model parameters given some data? And to find that, then you need the probability of the data given some prior parameters. And then you divide that by the probability of the data itself. But then the probability of the data is a normalization term, and it's usually very difficult to compute. And so to be able to compute this probabilities over here, then we resort to using the MCMC or Hamiltonian Monte Carlo, which is another variant of the MCMC, to actually approximate this, find these parameters over here. So what happens is that at the end of this, whenever you calculate these parameters, what you're getting is not a single value, like I said, but you're getting a distribution of parameters, because the probability, you are saying that what the probability of the parameters given the data, so you're getting some probability distributed function. And so whenever you make your predictions, you'll be getting something like this for a prediction. Instead of getting just one value prediction, that maybe I'm forecasting VCI for 4 weeks or 6 weeks, and the 6-week VCI is going to maybe 50% or 40%. This time around, you're not getting that single value, but you're getting a distribution of values, as you can see over here. And from that distribution of values, you can actually calculate the credible interval within which that your forecast lies. You can actually calculate the mean of the forecast to get the value of your forecasted value, and then, or the actual figure of your forecasted value. And so in this case, for instance, here's our forecast. This black line here represents our observed value, which is the true VCI for that particular time point, 6 weeks ahead. And this is the mean predicted. And the good thing about this is that you can still see that within the distribution, our observed value still lies within the predicted distribution. And so we are not too far off from the predicted value. And so we can say that, okay, our predicted value lies within this range, which gives some uncertainty information that, okay, we are not saying that the predicted value is just some single value, and we don't know, the range in which it lies. But then in this case, we can tell that, okay, the predicted value lies within some range. And so we are not always too far from the observed values or the true values, if in case we observe the value at the predicted time point. So using this model, we brought in, like I said, the precipitation so much, and then we also trained the model using the same rolling window training thing or cross-validation method that I showed earlier on. And we were able to come up with some predictions. Now, here, for instance, are some of the results from that model. So here, the results here are just showing some comparison between also just like we saw earlier on, we're just showing some comparison between the true VCI and the VCI forecast. But then what I did over here was that because previous models were doing very well, or let's say the AR model was doing very well after about 6 weeks, what I did was to look at how this new approach that I'm using was going to predict from 6 weeks up until initially I said about 15 weeks, but then I realized after 12 weeks I was getting some very bad results. I stopped at 12 weeks, which was still very good though. So here you can compare the metrics you're getting over here to the metrics that we are getting from the BRDA model. You could see some improvement in the model. So for instance, if at 6 weeks we're getting 0.88 for the AR model, that 0.88 that we are getting, we are seeing that at 8 weeks rather for, or something similar to the 8 weeks rather for the BRDA model, which means there's some sort of a 2 weeks improvement or 2 week gain in model in prediction improvement. And you could see that trend that whatever you see 2 weeks before for the AR, we are getting that for 2 weeks ahead of the BRDA model, which shows that the BRDA model, with the addition of these other variables, improve the forecast range. And so then we can now forecast into, over a longer period of time instead of just up to 6 weeks. So we could forecast up to 12 weeks and give some information to pastoralists or whoever is monitoring drought in a particular area. And then it gives them ample time to prepare to go and mitigate, the drought condition that's about to hit these people or wherever they are, within the pastoral community. Now, the 2 weeks, there are approximately 2 weeks improvement I was talking about can be seen clearly in this. So here I just put the overall performance over here, and you could see that if you're able to draw an imaginary line over here, you could see that the R-square value that we are getting for, let's say, the BRDA model at 8 weeks is similar to what we're getting for the AR model at 6 weeks. So you could see that improvement over there. Now, one other thing you could see the improvement in here is the ROC curve, where we're trying to look at the hit rate and whether there's a false alarm or a true positive rate. You could also see that improvement in there, that the AR models had slightly higher hit rates compared to the AR models. Apart from when it got to 12 weeks, we could see that, well, there's the lines were not too separate, but then which is expected that as you move along as you predict more, the prediction power actually reduces a bit, but then it's still a good prediction at 12 weeks. I mean, if you compare that to the R2 score and also the RMS, you could see that generally the errors here were lower compared to the AR model.
Sorry.
One other thing we also wanted to look at was forecast reliability. And usually, if you look at what I tried to do over there was to bring in the weather forecast. So every time you're forecasting the weather, you always see this thing that there's a 70% chance of rain or there's a 60% chance of rain. So instead of just predicting that VCI value is maybe 40 something or 50 something, I also wanted to bring in some information that would give you the chance of that being true or not, right? And so what we did was to calculate what they call the forecast reliability. Yeah. So what we did was to also, just like the ROC, binarize the predictions into zeros and ones, and then look at the probability of that forecast happening, and then comparing that to the actual observed frequency for that particular period in time. And so here, when we say maybe we predicted this chart you're seeing here is drought. That is where we looked at, first of all, we looked at the seasons. And so for this particular plot, we're just looking at the dry season where there were low rains, so the OND period or the October, November, December period where there were low rains. And sorry, yeah, okay. Wow, okay. So then I'll just jump into this, and then so one other thing we looked at also was to look at how well the additional variables were contributing, and you could see that lag precipitation was contributing a lot to the improvement of apart from the lagged VCI itself, the large precipitation was also contributing a lot to the model. But then one other thing we noticed was that within a region, there are variations. So initially we were just, we take a region and then calculate the whole pixel value for that region and then use that for the forecast. But then when you take a region like, for instance, over here, you can see that this map here is the agroecological zones. You can see that there are differences in the agroecologies within a given region. So instead of just aggregating all the pixels, why don't we bring in some form of hierarchy? So maybe we train the model such a way that different parameters are learned for a zone where it's tend to be arid, and a different parameter is learned from a zone where it's supposed to be semi-arid. And the question we wanted to ask ourselves here is that if we separate the parameters, or if we learn the parameters at the hierarchical level or in some stage, can we improve the forecast? And so this is when the hierarchical Bayesian model came in. And basically we were just trying to see for the BRDA model, we used a no pooling approach where we separated the data sets. But then for this one, we used a partial pooling where we pulled all the data together. But then in trying to parameterize, what we did was to learn a global parameter for all the different zones within a given area, and then also learn the individual parameters for the individual agroecological zones for the individual land cover types within that area. And what you could see from the results is that, yes, with that, you could see that the hierarchical Bayesian model also gave some better predictions compared to the BRDA model, because at this time around, we were also incorporating some spatial differences within the model. And so you could see some further improvement within the model, and you could see that across a lot of the metrics that we looked at. So for instance, if we look at this one where we looked at uncertainty, the uncertainty basically we are looking at how wide the forecast interval was compared to if you look at the hierarchical model, you see that there's a thinner uncertainty. And if you look at this one, the uncertainty is quite wide around the predicted values. And so you can see that the hierarchical Bayesian model did weigh, and this metrics here actually measure how wide or how slim those uncertainties are. So if you look at this MPIW that measures the mean prediction interval, you could see that it's lower for the hierarchical model compared to the BRDA model. And one other thing you could tell is that when it comes to predicting the forecast reliabilities, whereas the BRDA model will tell you that the probability of a drought happening here, this is the 35 line, the probability of a drought happening here is low. You could see that the hierarchical model was telling you that the probability of a drought happening here, which is where the actual prediction fell below 35, was very, very high. And so this tells you that hierarchical models were doing a better job compared to the BRDA models. So then what then are the policy implications of this? What this means is that these models have the potential of being able to come up with being able to use to develop some early warning systems for adequate forecast of vegetation condition. And currently our GP model is being used by the NDMA, the Kenya Rangeland Trust, and the Kenya Red Cross in their dashboard for monitoring droughts. And talks are currently going on so that these other models that are also worked on, which is the BRDL and HBRDL, to be used in the trigger phase of the early action protocol. So that these models will then, at the trigger phase of the early action protocol, that is when drought is triggered. That is where they start working towards, addressing some of the issues that are addressing or coming to the need of people who are likely to be affected by the drought condition. Now, future work basically, currently everything is based on pixel. We are pixel based, and we are just predicting single time series values at a time point ahead. What we are planning to do in the future now is to redo the pipeline so that instead of just taking aggregate over a region and predicting a timeline, what we want to do is to make it spatial so that at the pixel or the world level, so that when you take an image, you can see how VCI prediction is within a spatial scale. So in conclusion, yes, drought early warning systems are essential to ensure resilience in pastoral communities. Earth observation and machine learning prevents like a cost-effective way of doing this, because you don't need some of these earth observation data. Most of them are free to access, and so for developing countries, for instance, who don't have a lot of the resources, this is a cost-effective approach to monitoring drought. And then the Bayesian context as well helps a lot because it provides a robust framework for forecasting and also assessing forecast uncertainties. So thank you very much for this. I'd like to acknowledge my supervisors, Seb, Vedram, and then also thank Anna and Lizzie for all their support during my PhD. Then also thank Dara Big Data. Thank you very much. That's the end of my talk.